The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
This is, to give you a brief overview before we start, this is a session that is co-sponsored by 3 committees: 222, corrosion; 228, non-destructive testing; and 444, structural health monitoring, which is an existing committee with a new name and a new kind of vision. I'm John Popovich. I represent 444 committee. My co-moderator today is Mohammed Burgas. He represents 228 committee, or maybe I had switched that around, one of the two. And in the second session in the afternoon, we'll have Burkan Yusgor, who represents the 222 committee. So this is a session on electrical methods of all types, electrically based methods to kind of characterize concrete. And you can see the learning objectives here. I'm very pleased with the collection of papers that we were able to get, presentations, I should say, today. All the speakers in this first session are here, and we will try to run on time, so we should start on time. So I'd like to introduce our first speaker of today. And our first speaker is Professor Michael Thomas, professor from the University of New Brunswick, well known for his work on concrete materials, especially degradation mechanisms and repair and service life prediction and so on. We're very pleased to have him give the first talk today.
Okay, thank you. Okay, I'd like to start off by acknowledging my co-authors, 2 students from University of New Brunswick, Ted Moffat and Wang Yi, and David Smith, who graduated from UMB with his master's in 2004, and it's taken me 9 years to summarize his work. I'm a bit behind. But Dave has written a master's thesis on this that gets into the nitty-gritty, and if anybody wants a PDF copy of that, please catch me after this presentation. I can send you one. And actually, Dave's work was funded by the PCA under one of their fellowships, so I'd like to acknowledge PCA as well for the funding that went into a large part of this work. I was going to talk about the various electrical methods that we have for estimating the chloride resistance of concrete. And then late yesterday afternoon, I realized I only had 15 minutes, and I kind of almost had a heart attack and had to delete half my slides. So I'm going to focus on resistivity measurements, since that seems to be what a lot of people are doing now. But we have done a lot of work on migration tests where we actually measure the physical chloride movement under an electrical gradient. Doug Hooten and myself worked for the Federal Highways on developing a rapid migration test as well. And a lot of that work has been published in Kyle Stanish's thesis and also in the Federal Highway report as well. So again, I'd be happy to pass that on if you wanted to track down some of that information. Measuring the electrical resistivity is a pretty simple thing to do, and I thought since I was the first one on, I'd just give a little bit of background information so that you know what's going on. We can measure the electrical resistance quite simply by measuring the current flow under an applied voltage, and then we can measure, and of course the electrical resistivity is a function both of the material properties but also on the dimensions of the sample. If we want to measure the resistivity, that it should theoretically be independent of the size of the sample, and we take account for that by taking into account the sample geometries you can see there. That slide shows a very, very simple way of measuring electrical resistivity using a direct current. It is preferred to use an alternating current for doing this, and there's various devices available for doing that, and it's also quite simple to have one made if you have a decent electrical workshop. Electrical conductivity is just the reciprocal of electrical resistivity. Of course, the units are different, resistivity, I prefer to work in ohm meters. I think you'll see all kinds of different units today, ohm centimeters, kilo ohm centimeters, and everything. Most of my units are in ohm meters, and the reciprocal of that for conductivity would be Siemens per meter. And yes, I did pronounce that correctly. If you want to use, if you don't have an AC resistivity meter, then you can use DC direct current. Of course, there are polarization effects at the electrodes that have to be accounted for if you're doing a direct current measurement. Various different techniques for doing that. One of the simplest ways is to actually work at a different number of voltages and currents and take account of the polarization effects. Many of you probably know that ASTM has, of course, had a kind of resistivity or conductivity test on the books for a long time. It's known fondly as the rapid chloride permeability test. Whatever we like to call it, even though we use the words chloride permeability in its name, it is in fact just an electrical conductivity test. Quite simply, that's all you're measuring with that test. You just take 5 hours and 59 minutes longer than you actually need to. It's a very long-term electrical conductivity test. But that test has been modified recently to use the same equipment to measure the electrical conductivity. You see there a sketch of the apparatus. We can now take a full-size cylinder, 4 by 8 inch or 100 by 200 millimeters, and measure the conductivity of that specimen using the same equipment with the same 60 volts applied direct current, and then you just read the current instead of waiting 6 hours and seeing how much electrical charge flows. But essentially, you're measuring the same thing. Some of the other data that I'll be showing is actually based on using a 4-point probe. Again, I'm sure a lot of the speakers who are going to speak today are familiar with this. This is a technique that's been around for a very long time. It was developed by a guy called Wenner for measuring resistivity of soils and rocks. And it is a technique that can be applied to concrete as well. In this test method, you apply a current flow between 2 outer electrodes and measure the voltage drop across 2 inner electrodes. And it's supposedly relatively free of polarization effects, although there is some fancy modeling involved to actually come up with, to take account of the weird geometry of the experimental setup and the flow of the current and the equipotential lines as well. There are, as I mentioned before, there are different kinds of standard equipment you can actually buy off the shelf for doing these measurements. I noticed one of the devices is being marketed by ProSec, and they're actually up in the exhibits hall on the 3rd floor. So if you want to go and have a look at their equipment, they sell a very neat little handheld device like this thing here, which can usefully give you surface resistivity measurements. Various times we made our own equipment in our lab, and as I've said, it is relatively simple to manufacture your own equipment for doing this. Okay, I thought we'd have a look at some numbers again for people who aren't familiar with looking at resistivity. I've plotted resistivity there in units of ohm meters, and you can see how many orders of magnitude we go from 10 to the minus 8 for copper to 10 to the 14 for rubber. We're going from an electrical conductor to an electrical resistor. Concrete occupies some middle ground in that range there, as you can see. We're going from somewhere in the region of 10 to a million. So about 5 orders of magnitude. And I think this is a very important point to mention here. That range there is basically occupied by concrete in various different moisture conditions. It's the same concrete. So whenever we talk about, you can see there, saturated concrete there is somewhere around 50 ohm meters. That would be a typical result for a straight Portland cement concrete without any blending materials in there like fly ash, slag, and silica fume. But just by drying that sample, reducing its moisture content, we can change the output, the result we get. So you really have to remember that resistivity is a function of the moisture content, and if you're not measuring saturated samples, you're really wasting your time because the result can be meaningless. Typical range for values for saturated concrete is in the range of about 10 for really bad concrete to about 1,000 for really good concrete. So the really bad concrete would be the kind of concrete you might find in a residential foundation without any fly ash, slag, or silica fume, and a really good concrete might be something you might find in a bridge deck with silica fume and slag or fly ash, and also in concrete like that that's very mature. So that's the kind of range of values we can expect to see. If you plotted the same thing for bulk conductivity instead, remember I said the conductivity is just reciprocal of the resistivity, we would see we get obviously different numbers, but a similar kind of range. Of course, the difference is when we're using resistivity, we want to see high numbers. When we're using conductivity, we would rather see low numbers. So just try to remember that. For those of you who are really familiar with the rapid chloride permeability test and like to talk in terms of coulombs, if you took a concrete with a resistivity of about 180 ohm meters and you actually then put 60 volts across a 4-inch diameter by 2-inch thick disc like you do in 1202, you would get a current flow of around about 1,000 coulombs. So your 1,000 coulomb concrete that lots of the DO2s like to use is equivalent to about 180 ohm meters, or about a 5 millisiemens per meter. So just to give you an idea for where these values sit. Why do we measure the electrical resistance of concrete? What's this even telling us? I mean, if we're not actually using concrete for streetcars where we actually might want electrical resistance to stop stray current flow, why are we actually interested in the electrical properties of the concrete? Well, it's fortuitous that the electrical resistance of saturated concrete, again, I'm talking about saturated concrete, is dependent really on two things. One is the pore structure. It's dependent on the volume of the pores and the size and the connectivity of those pores as well. But it's also dependent on the composition of the pore solution. The solid phase of concrete is such a pore conductor that the pore solution just dominates its conductance in saturated concrete. So there's two things that control the conductivity or resistivity: the pore structure and the pore solution. Chloride resistance, on the other hand, and I don't think I have to explain why chloride resistance is an important property of concrete. Chloride resistance also depends on the pore structure. Depends on the volume, the size, and the connectivity, the tortuosity of the pores. But it also depends on the composition of the cement hydrates in this case and their ability to bind chlorides. So there is a very big similarity to the two measurements. They're both strongly dependent on pore structure. And that means you can use resistivity as a surrogate for chloride resistance. But as long as you bear in mind the differences, that in one case you're very dependent on the pore solution composition, in one case you're depending on the binding capacity of the hydrates. And this means that we can see some fairly broad differences between these measurements for certain concretes. So we have to bear that in mind. So I'm going to compare some data for resistivity measurements, rapid chloride measurements, whatever, and also I'm going to compare this data with actually measuring the chloride diffusion coefficient. I'm just going to show you a few data for this. We've written papers on this, so I don't want to dwell on it too much. This shows a data dump comparing the rapid chloride permeability value with the diffusion coefficient for about 83 different concretes. I say actually 83 is a fairly precise number to say, about 83. It's 83 different concrete mixes. And you can see there is a broad correlation. It's certainly not a perfect correlation. Reason we don't have a perfect correlation, of course, is one is, it's the cussedness of concrete. We always get lots of noise when we measure concrete properties. But the other reason is because of the difference in the pore solution composition. You can measure two concretes with the same chloride resistance that can have very different pore solution conductivities. Silica fume is an example of a material that will reduce the chloride resistance of concrete, but it also has a very significant impact on the pore solution and reduces the conductivity of the pore solution too. So you'll get a much bigger reduction in electrical conductivity than you will, say, in the diffusion coefficient. You've got other materials that work the other way, things like calcium nitrate inhibitors, which will increase the pore solution conductivity without necessarily changing the pore structure or its ability to resist chlorides. So we have to bear in mind that we're not measuring exactly the same thing, and as long as we keep those assumptions in mind, I think it's a reasonable thing to do to measure the resistivity. I'm going to flick over that pretty quickly. If you compare the Coulomb value, the 6-hour rapid chloride permeability test result, with an electrical resistivity measurement made on the same cylinder, you'll get an almost perfect correlation because you're measuring exactly the same thing. It's just that you're taking 1 minute or 6 hours to do it. And it's your choice which one you use. But there really is obviously an almost perfect correlation. I'm just going to show you just a few data points that shows you the good correlation again between these two tests, and I just want to move on to just some of the limitations very quickly. I'm just going to show you some data from Treat Island. These are concrete blocks that have been at Treat Island for 25 years. Then we bring them back to our lab and we do various tests on them. One of the tests we do is to simply measure the electrical resistance of the block before we even test it, just simply using a 4-probe surface meter. Then we go to all the work and effort of cutting cores in those blocks, profile grinding them, and calculating a chloride diffusion coefficient for them. And as you can see here, when I compare those two sets of data, I get a reasonably good result. Of course, a reasonably good correlation. You're crossing many orders of magnitude with both measurements, of course, and you can see the impact of having a supplementary cementing material in there. But I did also want to reflect on some of the things that start to skew this relationship between diffusion and electrical resistivity. One of them is carbonation. When the concrete carbonates, the pore solution composition changes dramatically. An uncarbonated concrete is dominated by sodium, potassium, and hydroxyl ions. Typically, its pH is somewhere in the region of 13.5. When you carbonate concrete, its pH of its pore solution drops to around 8. And the pore solution composition is totally, totally different. And it will look great from an electrical resistance measurement because the pore solution is non-conductive, or virtually. So we will definitely see carbonation will give you this apparent increase in the electrical resistivity, which is not real. In fact, if anything, you've very often increased the chloride penetrability because you've lost binding capacity of some of those hydrates. Now, it's true that carbonated concrete tends to have a denser pore structure, so those two things might come. But there's one thing that can have a big effect. Another thing is leaching. If you take small concrete samples and you store them in tap water or even lime water for a long period of time, what you'll do is you'll leach the pore solution out of the concrete and replace it with a relatively low conductivity pore solution. And hey, guess what? It looks like you've got increases in electrical resistance, which aren't real. Really, you should try to store your samples in a model pore solution if you really want to see what the effect of maturity and aging is, independent of the leaching that's going on. When we've compared in the past, we've compared surface resistivity measurements that we've actually measured on big blocks of concrete, and we've compared that to surface resistivities made on cores taken out of the concrete. What we can see at a relatively early age, the surface resistivity of the bulk concrete is similar to the surface resistivity of cores extracted from there. But with the passage of time, when I think we've got 2 or 3 years here, what we see is the surface resistivity increases more because you've got combined effects of drying, leaching, carbonation, all of which will tend to increase the surface resistivity of your exposed concrete without necessarily impacting the bulk resistivity of cores extracted from that concrete. Finally, I just want to, another thing that's going to impact your results to a great extent is embedded reinforcing steel when you're making field measurements. Very, very significant impact. Very, very complicated because it's going to depend on the geometry of your reading and the geometry of your steel. And so if you want to find out more about that, read Dave Smith's thesis because I don't have time. Finally, the last thing, and I promise you it is the last thing, another thing that we'll notice is with electrical resistivity measurements, usually the matrix has a much lower resistance than the aggregate, usually. And what this means is if you change the amount of paste in your sample, or you change the amount of aggregate, you're going to see a fairly significant difference in the change in resistivity. The more paste you've got, the lower your electrical resistance is going to be. Or I should say the more aggregate you've got, the higher electrical resistance is going to be. And this won't have the same impact on chloride diffusion. Chloride diffusion will be dependent mainly on the water binder ratio of that paste rather than the quantity of the paste. So it's just another little thing I thought I'd throw in there. Oh, I did say fine. Finally, be very careful when you start looking at different cementitious systems. We've built up all our correlation between chloride diffusion and resistivity based on Portland cement systems, with or without SCMs. When you start to get into different cements, there can be a very different relationship. I'm just going to show this as an example here. This shows your charge passed. It's basically a rapid chloride permeability test as a function of different cement types. The last one on there is a rapid set cement based on Klein's compound and B-Lite, CSA and C2S. It gives you a very, very low Coulomb number, down about 1,000 or 1,500. However, it's highly non-resistant to the penetration of chloride ions. And the reason it's giving us a high resistance or low conductivity is because its pore solution is a very low concentration. And that is, I'm going to leave you on that slide. That slide there just compares different measurements with rapid chloride permeability tests, the scale we're used to, and just shows you the sort of target values you should be looking for electrical resistivity to give you a similar kind of measurement. I'm sorry if I took too much time, but I'm a slow starter.
No, well, thanks very much.
Thank you.